is still there.
So the agenda is right, like it hasn't been changed or anything. So it's
No,
like Danielle
it's
and
just that there is so Giulia Tozzi is not there anymore.
okay,
Not sure about Michaela Ishman, she has not applied.
they're virtual, so
But
we
they
can
are
just
virtual and so and they
Hello,
have
hello.
different
Yes, awesome. AGN.
What's your favorite animal?
AGN.
Is this set up to show the presenter notes or no?
What?
Is this set up to show the presenter notes?
I think so. Yeah.
Yeah.
Yeah. It is. Yeah.
I can see my notes.
Yeah, you can.
If it's PowerPoint.
Key.
Then I don't know.
Then I'm not sure. Do you know how to do that in Keynote?
What do you mean?
Like how to do that in Keynote? Because like we managed to do that for PowerPoint, but not for Keynote. Like the presenter mode.
Okay. It's fine. I can just have my laptop next.
Do you have the presentation? Maybe you can like quickly try. Yeah, that's Rich, right?
Yeah, I can download one by one because it's not downloading.
Oh, so the entire
That's
folder
the
is not-
problem.
oh,
I'm
okay,
waiting
okay.
for download of the folder.
And it's rather large.
Oh wow. Okay. Yeah, because like Daniel's presentation is gigabyte, right?
Yeah. No, but we should be there.
Okay.
It's like all the pretty animations
Well,
that's
seconds
taking
left.
up.
Good.
I put some of Danielle's the MVPs of my talks there.
Who is the second speaker? Is
Megan Tillman.
download.
Maybe just download like Danielle's talk
Yeah.
first, and then you could run it in the
You can put
background.
that in the background.
Yeah.
Okay, so
Also the third one, I think. Yeah.
is the other one? Okay, here. Print Symposium. It's Friday. Human, okay. And Cochrane
Someone.
talks Friday. Okay. Cochrane here. So if I open it and I do play,
Yeah.
you see it's like this, and I don't know how do you change the.
Yeah, that's okay. I'll just keep my laptop with me.
Yeah, you can.
There is another presentation, right? Brian.
We can you so with this the second is Megan.
Second is
Brian,
Megan.
okay, I have all of them.
Brian
It's,
is.
because it's
Actually, no, you have it already. I
Yeah,
think
it's
maybe
here.
this one. Yeah.
But it's not downloading the folder, so I just downloaded
That's
the
okay, we
one
need to
for
do
the
one by
yeah.
And then we need the posters,
The
which is
posters is before I have to create the PDF. I will do it and I will upload
Okay.
it and we download it.
so it's 25 plus 5,
For Daniel it's 25 plus 5.
And the
for
rest-
others it's 12 plus 3.
12 plus 3.
Roughly, like as long as we stay within the 15.
Okay. Like exactly 9, so I think we are on time. There is like 2.
You go for the PPT, right?
It was open already.
Hello. Hello. For 1 or 2 more minutes.
Sure.
animations.
The
The presentation was like in GB.
Yeah, I'll try to keep an idea of what it's like. Yeah. Perfect.
Hello. Okay, we are in the final day of this amazing conference. So the first talk of the session will be Daniel Alcazar, who will talk about the role of AGN feedback regulating star formation in cosmological simulation.
Great, thanks so much, and thanks to the organizers for bringing us here. This has been really a wonderful conference. And thanks everybody for getting up so early. It's amazing that you are all here. So now that we are all well rested and full of energy to start the last day of the conference, so we are going to switch gears back to simulations after a few talks yesterday on the impact of AGM feedback in star formation in galaxies from the point of view of observations. So I'm going to be focusing on simulations and mostly on cosmological hydrodynamic simulations. So we want to understand how galaxies and black holes evolve in a full cosmological context. That's the goal here. And so broad picture, cosmic web in the background from dark matter only simulations. Galaxies form at the centers of dark matter halos. Galaxies, of course, are beautiful, complex objects with stars forming, stellar feedback shaping their local properties, as well as their global evolution via galactic winds. And then focusing on the center, we have supermassive black holes, which we believe play a key role in galaxy evolution. And so our question for the next half hour is, what's the impact of AGM feedback on star formation? This is what we're going to be addressing with simulations. But of course, stars are not just going to be waiting to be quenched. So we may want to see whether stellar feedback may have any impact on black hole growth, which would also affect the impact of AGM feedback, perhaps. And then going on, we want to more broadly think about what are the drivers of black hole galaxy coevolution so that we can have a more complete picture. And then that includes also any plausible impact of AGM feedback on much larger scales, even on the clustering of matter on cosmological scales. And then how closing the loop here on even the impact of environment on galaxy evolution itself. So lots of scales here, lots of physics, very complex to simulate. So galaxies and black holes in a cosmological context, different levels of detail, different types of models that we can use. So on the far right here, we have abundance matching models and halo occupation models, where the idea is, you use dark matter only simulations to study the evolution of dark matter halos, and then you populate them with observed galaxies, so that just in a data-driven way, we can understand a lot about how galaxies evolve and also supermassive black holes. And then going towards the left in this diagram, we have models that incorporate more and more physics. And so I'm going to be focusing here on hydrodynamic simulations, which are sort of the models that are the most computationally expensive of the full spectrum, but then try to do as much as possible physics based on first principles. So we solve for the couple equations of hydrodynamics or magnetohydrodynamics and gravity. And then we have to include a lot of recipes, subgrid recipes to model star formation, stellar feedback, and so on. And in particular for black holes, these are sort of the main aspects that every simulation nowadays has to include. So we need to add initial black hole seeds. You have to decide in the simulation when and where and how many black hole seeds there are. This is still very uncertain. Then we have to think about the black hole dynamics. How do they interact gravitationally with other components in the simulations? Then we need to model accretion at a sub-resolution level, like how much gas should get down to the black hole if we know some properties on larger scales of the galaxy. And then finally, we need to decide how to model feedback, the power, the energy that is released from the accretion process, how this would couple, in what forms, with what sort of geometry. So a lot of this subgrid physics then will have a big impact on the predictions from models. So different types of cosmological hydrodynamic simulations. So very broadly, we can talk about large volume simulations. Think about 100 megaparsecs, something like that, where simulations can follow the evolution of thousands of galaxies. And then by necessity, these models are limited in resolution. So think about kiloparsec scale resolution, and then lots of physics happening at a subgrid level, lots of free parameters that we need to tune in these types of simulations. Then if we want to understand the internal properties of galaxies, we need to use something called zoom-in simulation. So we focus on a much smaller region of the universe, still in a full cosmological context. But in this case, the increased resolution allows us to model the physics in a lot more detail. And we've seen lots of beautiful talks using zoom-in simulations already. And then finally, a bit of a new approach where we go back to large volume simulations, which again depend on many free parameters for things like the efficiency of stellar feedback, AGN feedback. But now we take this to the extreme of running thousands of simulations, varying parameters as a way to characterize the range of uncertainties in galaxy formation models, and perhaps even use them to train machine learning models to make progress in problems in galaxy formation and cosmology. So first results here. This type of plot has been shown already. So we have the stellar mass divided by the halo mass as a function of halo mass. This is the stellar halo connection, which is sort of the observable, one of the main properties that simulations need to be able to match. And so in red here, we see abundance matching models showing that Milky Way mass halos are the most efficient at converting gas into stars. And then we have a few lines of different colors indicating results from modern large volume simulations, which provide really a very good match of this. And I like to emphasize that now we are used to seeing plots like this, but 10 years ago, things looked very differently. So this is really a big success, relatively recent, with large volume simulations able to match the galaxy halo relationship and galaxy stellar mass functions, cosmic star formation rate history, even the bimodality in galaxy colors. So a very big success. So what do we learn in terms of the physics? Most simulations conclude that stellar feedback dominates at low masses, galactic winds regulating star formation at low halo masses. But then that's not enough to stop star formation in massive galaxies, and this is where AGN feedback comes into place. So historically, AGN feedback was introduced sort of after it was realized that the stellar feedback was not strong enough, and then different groups then implemented different forms of AGN feedback to try and make this work. So now that we have reproduced observations, we can ask, okay, what's driving quenching? And then the idea is, well, here we can see a bunch of different simulations, the impact that they have on large scale. So this animation here is showing results from Illustris TNG, SIMBA, Ramses Code, Magneticum, Eagle, and Astrid. These are all large volume cosmological hydrodynamic simulations. They have all been run with identical initial conditions. The blue color here shows the gas density distribution, and then in pink or red you can see the temperature of the gas on large scales, basically highlighting how different predictions these models make in terms of the temperature or properties of large-scale gas. So these movies are starting back again. So we see that Ramses is the first one starting to heat gas out in smaller scales. And then at some point we have, so this is also caused by stellar feedback, a combination of everything going on. Then we have Simba with these very large scale, fast velocity jets that begin to heat up the intergalactic medium very efficiently. And basically, as you can imagine, the predictions, even though they are all tuned to reproduce the same galaxy stellar mass function, for example, the predictions are going to be very different relative to other properties. So we can ask, well, what's really doing the quenching? So it turns out that if you train a random forest to try to predict what's the best, to find out what's the best predictor of quenching in simulation, this is for Eagle, Illustris, TNG, Illustris and TNG, it turns out that black hole mass is the best predictor, which kind of makes sense because in simulations we have added black holes so that they quench galaxies, so it makes sense. Very interestingly, that seems to happen also in observations, so SDSS galaxies. Black hole mass also seems to be the best predictor of quenching at that level. But now let's go back to the question of physically. Now we want to use models to learn about the physics. So in terms of what's quenching galaxies, the answer is very different in the different models. Horizon AGN would say that the jet mode feedback is what is doing the quenching. Eagle would say that more like quasar mode feedback injected in terms of thermal energy, that's the quenching. The older Illustris simulation is radio mode hot bubbles that are doing the quenching. Romulus is back to spherical thermal feedback. Illustris TNG, the answer to this question is radio mode feedback, but in the form of kinetic winds, spherically distributed. Simba would be jet mode feedback, a little bit of X-ray heating. So they are all producing the same types of galaxies, very different predictions in terms of the physics that dominates. Not only that, all simulations need to use tricks that we don't like to talk about, but here is some of them. We make AGN feedback efficient because we need to do it. So we have to tune the feedback parameters so that they are efficient. Some simulations decouple the winds from the hydrodynamics, again, so that they are more efficient. Some simulations accumulate the energy so that when you release the energy at once, it has a bigger impact. Some simulations shut down radiative cooling, again, to make it more effective. So these are all tricks that we need to use in part because of the low resolution of large volume simulations. So Freyka showed this figure yesterday from Ruby Bright's very nice paper illustrating sort of the different impact that different models have on the circumgalactic medium. So very important to look at the CGM to constrain models. And so in terms of stellar feedback, simulations like Eagle has the strongest stellar feedback on the one hand, but in terms of AGN feedback, Eagle has the weakest AGN feedback, that's indicated by these lines here, while in terms of AGN feedback, Simba of these models have the longest range effect, okay? So this is gonna make very important differences in predictions for like the CGM and the intergalactic medium as well. So we can go even look at the Lyman alpha forest. So this is looking at the column density distribution of neutral hydrogen in the Simba simulation and Illustris TNG, and then even varying some parameters within each model. And then just to see that the predictions are quite different between Simba and Illustris TNG. That sort of makes sense when we think about how differently they are like heating up the intergalactic medium. And even with a given model, we make the jets in Simba faster or the galactic winds stronger. This has a systematic effect on many of these predictions. And then if there are any cosmologists in the room, which I don't expect, then it turns out that feedback has a big impact in large-scale clustering of matter. This plot is showing the ratio of the total matter power spectrum in hydrodynamic simulations divided by the same quantity measured in dark matter-only simulations. So basically quantifying how differently matter distributes on large scales when we add baryonic feedback. So if baryons don't do anything and just follow the dark matter, all of the lines will be, the ratio would be just 1 here. But then what happens is that on very small scales, at the scales of galaxies, gas can radiatively cool, so baryonic matter can cluster more than dark matter, so that's why we see these lines going up here. But then on larger scales, AGN feedback, stellar feedback is ejecting gas out of halos, suppressing power on larger scales. And then different lines are for different models, again highlighting that this is a big problem for cosmology. So basically, we still don't know which line is right here, which means that when cosmologists try to extract cosmological information from data like this, they have to stop at some scales and throw away a huge amount of data. So we need to learn more about this. So now we keep going. Let's look at the black hole galaxy scaling relations. So again, simulations can fairly well reproduce observations, in part because we tune the accretion and feedback parameters so that we can reproduce these black hole galaxy correlations. And so here you can see the black hole mass as a function of stellar mass for some of these simulations in a set of papers from Melanie Habutzi. And then the contour here shows sort of the region of this plot that is populated with data in the low redshift universe, and we have some observations from Brian Terrazas over here. And so besides reproducing the black hole galaxy scaling relations, interestingly, simulations predict that overmassive black holes tend to correlate with lower specific star formation rates. So the color coding here corresponds to the specific star formation rate in simulations. And so you can see that at fixed stellar mass, galaxies that have overmassive black holes tend to have lower specific star formation rates. And very interestingly, this is also seen in observations. Okay, so I think this is interesting results. Now we can use simulations to then learn whether this connection between black holes and galaxies, whether it evolves with redshift or not. So this is again from Melanie's work. Now the lines of different colors correspond to the black hole mass galaxy mass relationship at different redshifts. And if we ask the question, is there a redshift evolution in the normalization of the black hole galaxy correlations? Then these are broadly the answers. Answer number one, yes. Higher normalization at higher redshift. This is what is predicted by Illustris or ISON-AGN, maybe Eagle as well. But the answer can be also yes, but higher normalization at lower redshift. That's Illustris TNG. You can see that the colors are switching between Illustris and Illustris TNG. And then if we ask Simba, the answer is, well, maybe, I'm not sure whether there is evolution or not. So not really clear according to models, okay? So let's also blame observers a little bit. We can ask the real universe whether there is evolution in the M-sigma relationship or not. We know the connection between black holes and galaxies is established at very high redshift. I think there's broad agreement on this. But whether there is intrinsic evolution or whether we just see mostly bias is still not clear. This is one of the very early results from JWST with overmassive black holes found all the way to redshift 9. But then in this plot of black hole mass versus stellar mass with a compilation of all the data, the solid lines here correspond to results from the Trinity model. There's some sort of empirical, like abundance matching model that is constrained to reproduce many, many observations. The idea is that the intrinsic relationship at redshift 9 from Trinity is this line over here. It's basically no evolution at all, but then the green line and the purple line correspond to the same population of black holes, but just setting up higher limit threshold luminosities. So basically showing how bias can completely change the picture that we have, okay? Now, evolution is going to be very important for galaxies, so we really need more predictive models. Now, we can look at other black hole properties. So this is the black hole mass function, top row, then the evolution of Eddington ratio, so that's the accretion rate normalized by the Eddington accretion rate, and then the evolution of number density of AGN of different luminosities. So this is, again, different simulations making these predictions compared to data in gray color in each panel. So super busy plot, just take away. For some of these quantities, I think there is expected agreement between different simulations and observations because all simulations are tuned to reproduce the black hole galaxy correlation as well as the galaxy stellar mass function. So it makes sense that you end up reproducing the black hole mass function fairly well. But to me, it's more surprising that there is a good agreement in the redshift evolution of the average Eddington ratios with high Eddington ratios at higher redshift and then going down, and also the evolution in the number density of AGN. So to me, this is remarkable success, even though there are like sometimes orders of magnitude difference between models and so on. But given that the subgrid black hole physics is still super uncertain. So to me, this is, again, a success. So an example of very uncertain subgrid physics, so how fast black holes grow. So we are like 20 years now after the first simulation, hydro simulations, including black hole growth and feedback. Most models still continue to parameterize accretion using spherical Bondi accretion, so neglecting angular momentum and many other things. which we know are not a good approximation, and actually many models and simulations have shown that the predictions by Bondi can be literally orders of magnitude wrong, and very few simulations really have tried something different, and the question is, well, do we care about accretion or do we just care about feedback? And so the idea is, well, again, just going beyond reproducing black hole galaxy scaling relations, we can ask, what's the physical mechanism driving the scaling relations? Again, we want to extract physical understanding from simulations. So it turns out that systematically, all simulations that use the Bondi accretion then systematically predict that AGN feedback self-regulation is what drives the black hole galaxy scaling relations. This is sort of almost predicted by construction, while simulations that use accretion prescription based on gravitational torques and stellar non-axis symmetries, torque in the gas, removing angular momentum, is what drives the scaling relations in these other types of models, which connects more with the idea of a common gas supply for star formation and black hole growth. So basically, we have like completely opposite physical reasons in simulations that reproduce the same set of observations. So we need more predictive models. And now going back to this question of, where does AGN feedback versus stellar feedback dominate? So most models only need AGN feedback on high mass galaxies, high mass halos, but this doesn't mean AGN feedback cannot be important in dwarf galaxies. So let's look at black hole growth in low mass galaxies. These are results from FIRE simulations where we look at the black hole mass versus the mass of the stellar bulge, and we see that these are tracks for individual black holes and galaxies showing that black holes at early times have a hard time growing according to this model. And so this is because early bursty star formation is driving efficient galactic winds, kicking out the gas from the nuclear region, and this is not letting black holes grow. And then at later times with a deeper stellar potential, the gravitational potential can confine the supernova-driven winds. This allows disks to form and retain nuclear gas reservoirs, and black holes quickly converge. And this picture is seen actually in simulations implementing different feedback. So there is not full agreement, but many simulations are predicting this type of slow early growth, which may have very important implications for in what regime AGN feedback is important, growth of early quasars, and so on. But I'd like to emphasize that the early growth is still very uncertain. So this depends on the feedback and accretion efficiencies, on the initial seed black hole mass. So it's still possible that black holes could grow more efficiently in low mass galaxies, but there is the problem of the dynamics of black holes. So are black holes staying at the centers of galaxies or not? It turns out that large volume simulations, if we don't just artificially pin black holes to the centers of galaxies, it's very difficult to make them grow. So this is just showing that experiments with no artificial repositioning of black holes in some models make them to not grow black holes at all. And then higher resolution zoom simulations that resolve the clumpy structure of high-resolution galaxies show that the problem is real, and basically, these are illustrating the types of chaotic orbits of black holes that are scattered around by massive stellar clumps. And so it's really still a big problem. How is the black holes can sink and end up at the centers of galaxies growing efficiently? Some very interesting predictions from simulations of populations of wandering black holes, like outside of galaxies or sort of in the outskirts. And actually, observations also suggest that black holes in dwarf galaxies might be sitting like basically almost anywhere. Nonetheless, there is still room for black holes to grow more efficiently, but I'd like to point out this other very nice paper by Megan as well, where assuming a model like this for the black hole stellar mass relationship with this very strong kink, you can put that into an empirical model to predict the quasar luminosity function, and there is some evidence in this region over here for a preference for this type of black hole galaxy correlation versus a single power law. And in fact, when you fit the parameters, this type of model gets back about the right mass threshold for this transition. So very interesting indication that this might be happening. But nonetheless, low mass black holes in low mass dwarfs could still have a big impact. So some simulations do predict a strong AGN feedback in low mass galaxies. I need to speed up quite a bit at this point. And so I'll just very quickly mention that the higher the resolution of the simulations, the more difficult it is to build fully consistent models that can quench galaxies at the high mass end without blowing up the dwarf galaxies. And so the less free parameters that we have, the more difficult it is to make them work. And this is just some results from Sarah Wellons that did this Herculean effort of analyzing hundreds of simulations with different efficiencies, different models to identify what range of plausible accretion and feedback models can work out across the full mass range. Then we have the aspect of can AGM feedback be positive, not just negative? And so we've heard a little bit about this from Giovanni yesterday. Some beautiful observations suggesting that there could be star formation within outflows, perhaps some coexisting indications for positive and negative feedback in action. And there are actually a few analytic models and idealized simulations that suggest that AGM feedback can compress gas and trigger star formation. And some models predict very interesting implications, going from driving correlations between star formation and AGN to very strong star bus to explaining the black hole galaxy scaling relations to very extreme star formation rates, many, many things. Problem is many of these models have been very idealized. So my student Jonathan decided to take a look at this in high resolution zooming simulations of galaxies, including high resolution model for AGN winds, and basically concluding that local positive feedback happens, but in the overall negative. So the idea is that locally AGN winds can compress gas so that it reaches higher star formation efficiencies, but for the context of like a strong quasar winds, the dominant effect is negative. He's also seen some interesting signatures of what could be the strongest signatures for positive feedback. With very strong winds, we see in some simulations the formation of very massive stellar clumps, 5 times 10 to the 7 solar masses in only 25 parsecs. So maybe this is like a Godzilla-like cluster that we heard about a couple of days ago. And then we also had the first day about how under extreme surface densities, stellar feedback is not able to regulate the star formation. And so that's the regime that the AGN winds are taking this clump here. So very quickly, in only a couple of million years, all of the gas in this clump is compressed by the AGN winds, collapsing to form this very massive star clump before supernovae can even react. And then just a quick note about the efficiency of AGM feedback. It depends not just on the amount of energy that you inject sort of around the black hole, but also what's the geometry of the gas around. And high resolution models now predict that a lot of the wind energy can escape to the circumgalactic medium as soon as you open up a bit of a cavity. And so this is very important, not fully captured by all models yet. So this is the type of picture that comes out from high resolution models now with more modern AGM feedback, where again, perhaps even small cavities then allowing a lot of the energy in winds to escape. But then if we inject the same amount of energy and momentum, but with an older model where everything is coupled on the nearest gas elements, the effects are like dramatically different. And this type of model is still what's the most common in large volume simulations because we have low resolution. I am super, super late, and I'm going to scan through super quickly a few just highlights. AGN winds can also regulate central surface densities and stellar masses. Jets, very important, very difficult to model the jet physics in any level of detail in cosmological volumes, but a lot of beautiful work in idealized simulations of jets. We need jets to maybe precess or be able to inflate wide angle bubbles to have some sort of interesting quenching effects. Lots of detailed physics implemented in more recent accretion models that try to incorporate what we learned from accretion disk simulations into models, and then increase resolution. We heard a little bit about this from Freike yesterday for the CGM. It turns out we can also increase resolution to model black hole accretion and feedback more efficiency. So different codes now can increase the resolution more and more when gas gets closer to the black hole, to a level where we can begin to model accretion explicitly at subparsec resolution in a full cosmological context. And so this is really opening up, I think, a new avenue to study black hole growth and feedback. And these are just a few an example of how across the scales we can have now simulations that can consistently capture the full cosmological context and yet this accretion on very small scales. So I'm totally out of time, but we are getting down to the accretion disk. So this is just 100 Schwarzschild radii in a full cosmological context. This is sort of getting very crazy, and I'll stop here. Thank you.
Questions?
Hi, really nice summary. At the very end in that last simulation, it kind of looked like you were tracking something that was moving. So in that new simulation, is it not pinning the black hole?
Is it this one?
Yeah.
So that's right. So here conditions are very turbulent. This is modeling a high-redshift galaxy with very interesting dynamics. So this is what the black hole is doing actually. It's sort of orbiting of a scales of like tens of parsecs. It's interacting with like very clumpy gas and very strong non-axis symmetries in the stellar potential. And so we believe that's just normal star-forming galaxy, and this could be driving a bright quasar. Things that we cannot see in sort of a standard, like large volume simulations.
Awesome, thank you.
Yeah, thanks.
Right, so this is really compelling, and I'm excited to see what comes next of the simulations. But as an observer, I'm intrigued by what exactly we should be looking for in terms of direct evidence for the local positive feedback, but this global negative feedback.
Yes, great question. So I think, let me see if I can go back quickly. So some of the, I guess, observational indications rely on the spatial anticorrelation between regions that are dominated by winds and then increase star formation efficiency maybe at the edge of the cavity. And so I think there is already interesting evidence that the AGN winds are opening up a cavity, and then when the winds collide with the ISM, they might be triggering enhanced star formation. Now, to what extent the positive aspect dominates or not versus the negative aspect, very difficult to tell, I think, just from observations, because you cannot observe the same galaxy shutting down AGN feedback. And so I think, in simulations we have that advantage. We can simulate the same galaxy shutting down AGN feedback to then conclude that AGN feedback the dominant effect is negative. So I think we have to look for more detailed signatures in the simulations to try and back that. Yeah, great question.
Okay, we actually, okay.
In my opinion, there are reasons to believe that the black hole masses at high redshift might be overestimated by even a factor of 10. What would be the effect on the simulations? What would change?
Okay, so if we come up with a model that we make the black holes grow a factor of 10 higher, a higher redshift, that is smaller.
Black hole mass is smaller by a factor of 10.
Relative to what is observed, relative to the local scaling relation?
What is now? I mean, black hole mass is at high redshift, not 10 to the 9 or 10 to the 10, but factor 10 smaller.
Yeah, I mean, if black holes are under massive relative to the host, AGN feedback would be just much weaker. And so I think that could be a problem for the more massive galaxies, for galaxies living with stellar masses above 10 to the 10.5, maybe something like that. That's where we need the most AGN feedback. So if black hole masses are overestimated and in reality are under massive relative to the host, I think, it's only a problem in terms of reproducing galaxy properties at the high mass end. But the interesting constraints for black hole growth and feedback.
Okay, let's thank our speaker for a wonderful talk. The next speaker So the next speaker is Megan Tillman, who will talk about the interplay of AGN and stellar feedback in the camel simulation.
All right, can everybody hear me? Okay, cool. Hi, I'm Megan Tillman. I am a PhD candidate at Rutgers University. My advisor is Blakesley Burkhart. My title is different from what it says in the schedule. I'm very sorry. My abstract was very ambitious. I have 10 minutes. So let's go ahead and get started. I'm going to be talking about the interplay of AGN and stellar feedback, like a lot of people here. So first, let me tell you about the CAMELS project a little bit. I think we've heard about it a little bit in this conference, but just as a review, The CAMELS project is a set of over 10,000 simulations, N-body and hydrodynamical, exploring parameter variations of different simulation subgrid models. So this includes simulations like Illustrious TNG, Simba, Astrid, Magneticums, Swift Eagle, Ramses, Enzo, and there's plenty more that are planned for the future. They have pretty small boxes, so depending on what you want to do, this might not be large enough for you, but it's great for looking at trends. They have a particle resolution of 256 to the cubed, and this is their mass resolution. So because these simulations explore many different subgrid models and many different parameter variations, this is also a movie you've seen earlier in the conference, you can get very different evolutions of how the box looks. And in particular, you can see that the temperature of the IGM can change dramatically between simulations based on different feedback models, etc. So this really gives us an opportunity to study these different feedback models, especially since these simulations vary the strength of the different feedback models through different parameter variations. So, for context, what I normally do is I explore feedback effects on the IGM. So here I have CAMELS Simba, and we're looking at the temperature in the box and how it changes when you increase the strength of different AGN feedback parameters. You can see generally increasing the strength of the AGN feedback parameters increases the temperature in the box. This is something you might expect. But for due diligence, we also want to check that the stellar feedback parameters, how they might change the temperature in the box. You know, we might not expect them to because their stellar feedback's pretty local and it might not reach out to the IGM. But surprisingly, we saw that stellar feedback changed the temperature even more dramatically than the AGN feedback. And at first, this was really concerning because you shouldn't expect stellar feedback to do this. But then if you look a bit closer, you see, especially at the bottom panel, the temperature decreases as you increase stellar feedback. So, okay, it's pretty clear here that this must just be an indirect effect, and the stellar feedback's actually affecting the AGN feedback. So the black hole growth, it's seeding how much energy it's actually putting out into the IGM. So how can we confirm this? Why does the stellar feedback have such a dramatic effect? What is it affecting in the supermassive black hole model? So this is a lot of information, I apologize. It's quickly summarizing how the supermassive black holes are modeled in these different simulations. In particular, I'm going to be talking about Simba and Astrid today. And even though this is a lot of information, it's grossly oversimplified. If you want to know the full details of the model, you should go and look at the individual papers. But for our purposes, there's only two things that I really want to cover. First is how the black holes are put into the simulation. So as we heard in Daniel's talk, they are seated in the simulation, so this is very artificial. If you know a better way to do this, I'm sure the people who build these models would love to know. They are put into their hosts when they reach a certain either halo mass or stellar mass. And these seeds can be small or large, so in Simba they're slightly smaller, 10 to the 4 solar masses, and in Astrid they're slightly larger, but a little less large than they are in Illustrious TNG. The second thing I want us to look at is the amount of black holes that are in the low accretion rate mode. So black hole feedback is modeled in two different modes typically, high accretion rate and low accretion rate. And for low accretion rate, there's also typically a mass threshold. Sometimes this is directly applied. So in Simba, these black holes cannot produce low accretion rate feedback unless they are a mass of 10 to the 7.5 solar masses or higher. In simulations like Illustrious TNG and Astrid, it just happens that the low accretion mode is triggered when the black hole is about 10 to the 8 solar masses. So we're going to look at the fraction in the low accretion rate mode that tells us kind of how massive the black holes are in the box. So what am I showing you today? We're going to look at first, that was weird, total number of supermassive black holes seated in the simulation, so total number of black holes in the box. This is a good probe for galaxy and halo growth because your host has to hit a certain mass threshold before the black hole is actually placed in the simulation. We're also going to look at, I don't know why it's doing that. Okay, we're going to look at the fraction of supermassive black holes in the low accretion rate mode. This mode is exclusive to more massive black holes typically, so this will let us know how much our black holes are really able to grow once they're seated. Transitions. These are the quantities we looked at in this paper. This is one of the papers where we were looking at how black hole feedback might affect the low redshift Lyman alpha forest. I'm just plugging this now because I want the observers to stay interested, because I will talk about this more later. All right, so first let's look at CAMEL's SYMBA, and we're going to look at the stellar feedback variation specifically. So kind of switching the script, we're going to look at how stellar feedback affects AGN feedback rather than the other way around. So the solid lines here are the total number of supermassive black holes in the box. The dashed lines are the fraction of these black holes that are in the low accretion rate mode. And the red lines are for a high value in that parameter, and the blue lines are for a low value in that parameter. On the left, we're varying supernova mass loading. On the right, we vary supernova wind speed. So this is like the only plot I'm showing you in this presentation, so hopefully it will be mostly followable. So first, let's look at the number of black holes in the box. We can see when we increase the stellar feedback parameters, we generally see a lot less supermassive black holes being seeded. So we see a lot less growth of our galaxies. So stellar feedback's regulating itself. We also see for supernova mass loading that we have slower early growth of the black hole. There are less massive black holes early on, but then these black holes are still able to catch up and grow at later times, but there are still much less black holes in the box, so you are still not going to have as much feedback going on. For the supernova wind speed, we see at all times that the supermassive black holes are growing slower. They're not able to reach higher masses. So we can see in SYMBA that strong stellar feedback reduces galaxy growth and thus limits AGN feedback. So it's important to kind of think about how these feedback models are intertwined. So let's move on to ASTRID. The only difference here is that the first parameter varied is the energy per unit star formation rate. The one on the right is still supernova wind speed. So we see similar trends here. There are less supermassive black holes being seeded in the box. For both cases, more so for the wind speed. And we have smaller mass black holes. So our halos can't grow as effectively, and our supermassive black holes, once they are seeded, also can't grow as effectively. So strong stellar feedback, again, is limiting halo growth and thus limiting AGN feedback and black hole growth. So as I promised, well, I broke my promise that I'm only showing you one plot in this presentation. This is the second plot. But here is what I mainly work on, is how we might be able to see these AGN feedback effects in the Lyman alpha forest. This could be a good observational probe. And we can see here the column density distribution of the neutral hydrogen in the Lyman alpha forest. Thank you, Daniel, for plugging this plot in your talk. And we can see as we increase the supernova wind speed, we have more neutral hydrogen in the forest because those AGN are not able to heat the IgM as much, and so it's not able to ionize as much hydrogen. And you get the opposite effect when you decrease the supernova wind speed. So if we can observe these effects, this would be amazing, but we have to find a unique effect that the AGN feedback has on the IgM and not something that can be degenerate with other things like what UVB model you use. All right, so what is my conclusion? I'm doing great on time, so I'm gonna just take my time on this slide. So the interplay of AGN and stellar feedback is very complex. This is something that you all probably know already. Stellar feedback can suppress AGN growth. AGN feedback can suppress stellar growth. And we need to be tuning these AGN and stellar feedback models simultaneously. Because if you make your simulation with just one feedback model and tune that to match your observational parameters as best as you can, you're going to add in your other feedback model and then maybe mess everything up. So we really need to be thinking about these models at the same time. And in particular, supermassive black hole seeding can be very sensitive to feedback parameter tuning. So it's already pretty unrealistic the way that we seed supermassive black holes in the simulation, and there's really not a good way around that at the moment. But better understanding how this happens will be necessary to better improve those subgrid models. And this will involve better understanding how supermassive black holes are formed in the actual universe. Not something I'm an expert in, but something I would love to talk to people about if they work on that. And finally, the Lyman alpha forest may be a good observational probe to constrain these different feedback models if we can find a unique effect. And I'll plug here that for Habitable Worlds Observatory, which I'm very excited for, please vote for a far ultraviolet spectrograph with high enough spectral resolution to observe the forest. In particular, we do not have any observations of the Lyman alpha forest at redshifts of 0.5 to about 1.8. So it would be fantastic if we could fill in that observational gap, especially because in the work that we have been doing, we see that the AGN feedback effects really start to kick in that redshift range. And so if we're going to find a unique effect in the Lyman alpha forest, it's probably going to be right around there. And so it would be really good if we could study that. So with any luck, this will be up before I get tenure. I'm still very early in my career. And thank you so much for listening.
Thank you so much. So let's have questions. Questions.
Hi, really nice talk. I just had a clarifying question for the Astrid number of seeded black holes. It seems like it turned over and decreased. Is that like black hole mergers or what's causing that?
Yeah, I have to assume so. So then much of the black hole growth also might be kind of due to mergers as well.
Great, thanks.
More questions.
I also have a question about the black hole seeding. So if you increase or decrease mass, does that change the quantity of black holes that you would see?
Yeah, if you decrease the mass, I'm sure you would see much more. Like I know with Astrid compared to illustrious TNG, I didn't show illustrious TNG here for time, but you do see more in Astrid because it has a slightly lower halo threshold. And I know people look at how changing the black hole seed mass might affect feedback and stuff, but that's not something I look at, but I know other people look at, so yeah, sorry about that.
Any more questions? Okay, let's thank the speaker.
No, I just wanted to see my timer and my notes. For some reason, it wouldn't work on here.
Okay, so our next speaker is Rachel Cochrane, who will talk about modeling the impact of AGN-driven winds on galaxy sizes.
I think so. Okay. Yeah, sounds good. Okay, so thanks very much, and thanks for the organizers for having me. I'm going to be presenting some work I did last year in collaboration with Daniel Alcazar and a student at UConn, Jonathan Mercedes Feliz. We've been running simulations within the FIRE collaboration to model feedback from an AGN and look at the impact of AGN winds on a host galaxy and its surroundings. Okay. So first of all, I want to summarize the FIRE model that kind of forms our base. So with FIRE, we're able to resolve galaxies on scales of tens of parsecs, down to the scales of kind of giant molecular clouds. And really critically within the FIRE collaboration, we're accounting properly for various feedback processes that affect galaxies. So the FIRE galaxies I've been using, although there are kind of a wide suite of different masses, I've been most interested in galaxies that reach masses of about 10 to the 11 solar masses by redshift 2. And these galaxies also model an accreting black hole via Danielle's gravitational torque model. One of the motivations for the work that I want to present today was the challenge of matching observed galaxy sizes for the most massive galaxies simulated in FIRE. So this is a figure from work we did to compare forward modeled rest frame optical sizes of FIRE galaxies at different redshifts, shown here by these symbols, with some observationally derived relations from Van der Waals' 2014 work, shown here in the kind of contours. And you can see that our FIRE-modeled galaxies actually fall quite a bit below these observationally inferred relations, particularly as we go from the higher redshift snapshot to the lower redshift snapshots. So we set out to kind of investigate the cause of this and look at whether implementing AGN feedback in FIRE can help us agree a bit better with the observations. So I'm going to tell you today about kind of a controlled experiment we did on one of the massive FIRE galaxies, adding some AGN winds. So these are the evolutionary tracks of this one galaxy. This is stellar mass versus redshift, star formation rate versus redshift, gas depletion time, and then intrinsic half-mass radius within the FIRE simulation. And you can see that this is a massive galaxy, as I said, reaching about 10 to the 11 solar masses by redshift 2. And like the other FIRE galaxies, this one shows quite bursty star formation. So star formation is happening in bursts. The feedback from a burst drives gas out, kind of preventing star formation for a while until kind of the next collapse of gas. And I want to focus in on this single point in the galaxy's history marked by this red cross, which is where the galaxy undergoes its most, around the time the galaxy undergoes its most strong starburst event. So the star formation rate here reaches about 600 solar masses per year, very high gas inflow rates, and we see actually that around this time, the size of the galaxy changes quite dramatically. So the half-mass radius is decreasing from a couple of kiloparsec right down to kind of 0.3 kiloparsec. So, contracting by a factor of 10 over scales of just tens of mega years. And so at this point, we see that the stellar feedback within the FIRE model isn't able to regulate the star formation, and the gas is collapsing into this very, very compact starburst. So this motivated us to study whether some kind of quasar-driven feedback could help regulate the starburst and prevent this collapse. So we implemented a new model to add AGN-driven winds within this FIRE galaxy at redshift 2. And the black hole is modeled as a collisionless particle, mass around 10 to the 9 solar masses, located near the center of the galaxy. And we assume that the accretion rate is constant at a fixed fraction of Eddington for the duration of this simulation, which represents a luminous quasar phase lasting about 40 megayear. So we're not, modeling this across the cosmological timescales that the FIRE simulations can span. We're just focusing on kind of this controlled experiment over tens of megayears. And then the outflow rate is some fraction of the black hole accretion rate, which we again can vary. So you can see this visually here. The black and white contours represent the density of gas particles that kind of come as part of our standard FIRE model. And then the colored contours show the wind particles. And something to point out is that these wind particles are modeled at very high resolution. So they're about 20 times higher resolution than the native FIRE resolution. And from left to right, you can see the impact of the wind on different scales. So from kind of hundreds of kiloparsec right down to the innermost 10 parsecs. So this figure now shows the total gas density from a face-on view on the upper panel and an edge-on view on the lower panel. And the benefit, as Daniel mentioned, of these very highly resolved wind particles is that you can really capture the impact of the winds on the gas geometry of the galaxy, regardless of what that gas geometry is. So we repeated this experiment, as I said, with different feedback strengths. So we varied the black hole accretion rate, and we also varied the mass loading factor of the winds. So this is kind of corresponding to different assumptions about the kinetic feedback efficiency of the winds. And in this plot, I'm showing the projected gas surface density from, I'm not sure we can see the timescale, but it's 0.2 megayears to 30 megayears. And you can see that for the weakest model shown in this line, there actually isn't much of a difference in the gas surface density between feedback, a model with feedback, and with no feedback here. But if you go down in feedback strength to the model with the strongest AGM feedback, you see that actually the gas is essentially all cleared out of the galaxy over timescales of tens of megayears. So we've been kind of using these simulations to look at a number of feedback-driven effects. Daniel already flashed up this work by Jonathan Mercedes-Feliz, and he was interested in whether we could see hints of positive feedback despite the overwhelmingly negative feedback. So here he's compared the star formation rate surface density as a function of radius for a model without the wind, so the standard fire model in blue, and then with a wind in orange. And you can see that the AGM wind is really clearing out this star formation from the center of the galaxy, but at the edge of the cavity, we actually do see a slight increase in the star formation rate density. So very small regions, small slices of positive feedback despite generally negative feedback effect on the star formation rate. And in the second paper, he looked at another effect he noticed, which was the formation of these very dense stellar clumps. And this only happens when you add the feedback in. So it's potentially some kind of observational tested feedback. But what I want to focus on really is the impact of the winds on that rapid compaction event. So that point at which we saw stellar mass assembling very rapidly and a very compact starburst. So this figure shows the stellar mass against time, and then the stellar half mass radius against time again for this galaxy over a few tens of megayears for different feedback models. So in gray, I'm showing the no feedback model, purple, very weak feedback, down to particularly strong feedback, 50% kinetic efficiency in orange. And you can see that the weak feedback actually doesn't have much of an impact on the growth of stellar mass here, on the stellar half mass radius. But if you go kind of up to the strongest feedback in orange, the galaxy really isn't growing much mass, and the half mass radius is stabilized. And even for intermediate feedback cases like the green shown here, so this is 10%, 10 to 20% kinetic feedback efficiency, we're really able to stabilize this half mass radius at about 1 kiloparsec, so preventing this collapse to 0.3. But of course, we've been looking at kind of stellar mass within the simulation, and these simulations predict these beautiful kind of physical quantities like dark matter density, gas density, stellar density, which is not what we see observationally. Observationally, we have light, and even when we, hope to transform that light to stellar mass, it comes with all kinds of observational kind of uncertainties. So for many years, I've been kind of aiming to project these simulations into observer space, so essentially running radiator transfer on the simulated galaxies, so tracking the propagation of the stellar light through the galaxy's dusty medium to make predictions for the multi-wavelength continuum emission for these simulated galaxies. So I repeated this for this controlled experiment with the AGM winds, now able to look at the impact of the different wind models on the observable emission. So I plotted here a rest frame emission from UV to far IR, from left to right. So the top panel shows the starting point of our simulations, and then the bottom panel shows two simulations after 35 megayears, so one without the winds, and then one with the winds. And as you can see, there are some quite significant differences in the multi-wavelength emission between the two models. So when you don't have the winds, you see this very compact dusty starburst. We see very bright far IR emission. When you add the winds, the suppression of that compact starburst actually means that the far IR emission is both fainter and more spatially extended. We can also look at the rest frame optical wavelengths, which was the initial kind of motivation for this work. And here the effects are actually a bit more counterintuitive. So without your winds, the dusty kind of compact starburst obscures all the central light. So even though we have intrinsically very compact star formation, the emission is biased outwards. So you actually end up with light bias towards tracing the least dusty outer regions of the galaxy. When you have AGN-driven winds, you have more short wavelength light because you don't have that dust-obscured starburst, but then because there's less dust extinction, you have more in the center, and you actually, I guess the point is that the two models predict similar half-light sizes. So if we look at this in the frame of the ratio between the size with winds to the size without winds as a function of radius, of wavelength, sorry, we see kind of this strong trend with wavelength. So this red line shows the point at which the sizes are equal, and we see the strong trend. So actually at longer wavelengths, you're able to discriminate better between the model with winds and without winds. So I think I've been out of time for a little while now, but I'll just flash up my summary. So we've been able to implement AGN winds within the FIRE model. We find it's really important to capture the interaction between the wind and the host galaxy ISM. We're able to do this with very highly resolved, hyper-refined winds following the propagation from tens of parsecs right out to the CGM. We are able to regulate central galaxy densities as long as we have kind of near Eddington accretion and kinetic efficiencies of about 5 to 10% over timescales of tens of megayears. We see a central cavity. And then finally, the changes in subgrid models can have quite significant impacts on our predictions for observables. And it's really important to forward model if you want to kind of properly understand those predictions. Thanks.
Really amazing talk. Questions?
Hi, thank you for really nicely connecting the simulations with what we expect to observe. I was curious, in the simulations, a lot of times, as you showed, there's this kind of easier escape along the polar axis. Does the simulation implicitly assume the black hole spin and the galaxy disk are aligned, or do you allow for misalignment that can kind of drive more of the outflow and feedback into the disk and might kind of change where you're seeing feedback in the disk versus escape into the CGM?
Yeah, actually, I'm not sure of the answer to that at all. I'm not sure quite how the black hole spin folds in, but Daniel might know.
Yeah, I guess there is no black hole spin implemented in those simulations. Some simulations do include a spin, and actually these simulations implement the spherical symmetric winds, and so a lot of the collimation happens by the interaction with the ISM. But yeah, great point. In principle, we can implement winds that are collimated at the inner scales, and depending on the orientation of the disk, then it might be very interesting effect.
More questions?
So for the observables you showed, sort of the broadband emission, do you have the capability or any plans to look at, say, the emission lines due to photonization or maybe like due to shocks from the AGN wind?
Yeah, so I, as you kind of noted, I've been working mostly on the continuum emission, but we are kind of in the process of modeling emission lines. Doing the forward modeling, looking at both the star formation rate, impact on the gas, and then also some impact of the AGN itself to predict kind of IFU like data cubes that you can really look at how an AGN might affect those. So that's what led by NeuroEngine, Roy.
Any last quick questions?
As a follow-up to that, is there any plan to look at the to predict what we would expect to observe in terms of the kinematics?
Yes, yeah. So this is another component of that project. It will be very, very interesting to look at. Don't have results yet, but we will do within months, I think.
All right, let's thank the speaker again.
Brianne.
Our next speaker, hello, is Brianne, who will talk about the low redshift distribution of star formation in TNG 100 galaxies.
Yeah, so as you said, I'm going to be talking about this. The talk is going to lie in between today's session and the previous session because I'm kind of going to focus a little bit more on the environmental factors. But yes, I'm Brianne. I am a PhD candidate at Boston University where the grad students are currently on strike. This is going to be work that I worked on with my colleague, Olivia Curtis, and my advisor, Teresa Brainerd. So historically, simulations have actually really struggled to reproduce the observed distribution of star formation properties in observed galaxies. So on the left here, I'm showing the star-forming main sequence and stellar mass versus star formation rate for SDSS galaxies. And then on the right is the same distribution in the TNG 100 simulation. So now that the TNG 100 simulation is reproducing these global properties of star formation, I wanted to see if there were further tests we can do of the feedback models that are implemented in the simulation by now going into a resolved or local scale. So the slope of this main sequence is reproduced within 2 sigma. And so we're going to be hearing actually from Asa Bluck later today, but in this paper they looked at manga data to examine the radial distribution of star formation in galaxies. And this, I thought, was going to be an excellent test for the TNG 100 simulation. Now that it's getting these global properties, can we reproduce the resolved properties? And so I'm looking at TNG 100 specifically. It's this kind of medium box size because I need the best balance of resolution to sample size, because I am also really interested in low mass satellite galaxies, but in order to look at these galaxies on a resolved scale, I need enough resolution. So I'm in this medium box. And so what I've done is I've mapped the stellar particles in the individual galaxies and tried to make them as comparable to observations as possible. And in doing that, I am able to show that the TNG 100 simulation is reproducing this resolved main sequence where we're looking at the surface density of stellar mass and star formation rate. And we actually have a really good agreement between the 2 slopes that we obtain here between TNG and the manga data. So going further, I can look at now these azimuthally averaged radial profiles. So I'm showing TNG at the top and manga at the bottom here. And I should have said on this last slide that this distance from this line is this delta sigma SFR parameter. I'm going to show it once on this slide and then not again for this talk. I'm going to focus more on these age profiles. But the point I want to show here is that the TNG simulation is reproducing the distribution of these radial profiles in main sequence, Green Valley, and quenched galaxies. The exception is the starburst galaxies. You can see here that we have these slight positive slopes in star formation rate or negative in age, which is the opposite of what is seen in observations. And in
Spar and Springle, they found that it's really just because you need better spatial resolution in order to properly model starburst galaxies. But starbursts are a relatively small portion of my sample, and I'm really happy that the simulation is reproducing these distributions, which means that I can now look a little bit more at what is driving these distributions. And just a note before I get on to my more recent work, there is a significant difference in low mass galaxies versus high mass galaxies. So below about 10 to the 10 solar masses, you have these much flatter profiles compared to at above 10 to the 10.5, where you have these very clear signatures of inside-out quenching in these ages, where you have older ages at the center and younger ages in the outskirts. And Nelson et al. 2021 found that in the TNG simulation, at least, these inside-out profiles are definitely being driven by the AGN feedback. Okay, so talking a little bit about the high mass galaxies, and then I'm going to focus on low mass galaxies because I'm more interested in them. You can see here, when I separate out these galaxies by black hole mass, there's a difference in the radial profile shape. So for central galaxies and satellites, it looks fairly similar when we're looking in the high mass regime, where we have the most massive black holes have the oldest ages, but not actually the steepest slopes. That's in this next highest black hole mass bin. And that's because the galaxies with the most massive black holes are almost entirely quenched already. And so there's no longer star formation going on out here, and so those ages are going to creep up. I'm not going to show it, but you can also look at the cumulative feedback energy in the simulation, and we find very similar trends in that respect. So it really does seem like these profiles are being driven by the AGN feedback. But there is some environmental effects that can occur when we get to very high halo masses. So again, it's similar trends in the central and satellite galaxies, but it's a little easier to see in the centrals because there's just other things going on in our satellite galaxies. And I should have said, in my work, I'm defining satellite as anything that's not the most massive galaxy in a halo. But what we can see here is that in these most massive halos, this and then the purple line, you actually see a slight positive slope at large radii, and then this much flatter profile in the most massive halos. So if we compare that now back to the massive black holes, you can see that these galaxies are also entirely quenched, but they still have this signature that they were quenched from the inside out, versus the centrals in the high halo masses, where there's sort of inside out and outside quenching operating. Okay, so now I'm going to move to the low mass galaxies, because I think they're particularly interesting. And when we look at the low mass galaxies divided up by black hole mass, there's very little difference, there's very little dependence on black hole mass for these radial profiles. But that's not to say that the black hole isn't doing anything for these galaxies, because if you can see these blue lines, this is where no black hole has been seeded into the galaxy in the simulation, and they have much older ages than the other galaxies. So while the supermassive black hole is regulating star formation, it's not really driving this quenching ultimately. And so there must be other factors at play. So now if we look at halo mass for low mass central and satellites, we see actually very different things happening in the centrals and satellites. Now, for the centrals, the halo mass is correlated with the mass of the galaxy. But at very low mass halos, we have much older ages in the centrals, where there's no dependence here at slightly higher masses. Whereas for the satellites with the oldest ages are those in the most massive halos. And you can see some of this possible outside-in trend happening in a positive slope in that purple line. And then at the most massive halos, you get these older ages. So something different is happening here for the central and satellite galaxies. And for satellites, of course, the halo that I'm talking about is the halo of their host. And so there's some dynamic processes occurring where the satellites are interacting with the host's CGM. And we can also look at this in terms of local galaxy overdensity. This will predict the chances of galaxy-galaxy interactions occurring. And there's noticeably older ages in the largest overdensities, but it's not as significant as it was. And these are averaged bins. And the other thing to keep in mind is overdensity is correlated with halo mass as well, especially for the satellite galaxies. So there's a little bit of degeneracy there. But What I'm now showing you is the halo mass versus local galaxy over density for low mass centrals in pink contours, and then the low mass satellites in yellow contours. And then I've overplotted where the quenched low mass centrals are and where the quenched low mass satellites are, so we can understand a little bit about where these galaxies exist in parameter space. If they're not being quenched by AGN feedback, they're being quenched by some of these environmental parameters. And so what's interesting here is that the quenched low mass centrals are clustered at these low halo masses and high galaxy over densities, although there are some that exist throughout the rest of the parameter space. And my interpretation from that is that these galaxies, the low mass centrals, are being quenched via interactions with other galaxies where they are more susceptible to having their gas stripped away because of their lower halo masses and therefore lower gravitational binding energy. Whereas the low mass satellites that are quenched are clustered at the high halo masses. And my interpretation there is that they're being quenched by interactions within their halo. So I have a little bit of time to talk about what I've been doing now, which is looking at some of the change in star-forming properties of satellite galaxies after they've entered their halo. Because functionally, what is going to be quenching these galaxies is removal of star formation gas, or changing the gas from being star-forming to not star-forming. So I've just looked directly at the change in star-forming gas. And for low-mass galaxies, you can see this flatter outskirts when they've lost a lot of the star-forming gas. And if they've gained some star-forming gas, they have much younger outskirts. And for the high-mass galaxies, you don't see any case where they have really significant star-forming gas gain. But when they do, that gain is occurring in the outskirts. And so again, these results are very specific for the TNG simulation in the models. And this is not an observable, so it can't be a prediction. But those halo masses, the radial profile dependency on halo mass is. So the takeaway here is that these environmental changes are preferentially affecting the outskirts of these galaxies. And I think there's a few more parameters in terms of the star-forming gas and looking at gas fractions and metallicities that I'm interested in looking at, but I haven't so far. Okay, I'm running quickly out of time, but I just wanted to plot and show the distributions of quenched Green Valley and main sequence galaxies for low-mass galaxies and high-mass galaxies at the bottom. And you can see that the quenched population in high-mass galaxies doesn't really carve out its own region in these environmental parameter spaces because, again, they're largely being quenched by their own intrinsic black hole quenching. And, but for the low-mass population, this quenched galaxy is carving out this nice region in halo mass versus star-forming gas, where you have at high halo masses, you can strip more gas away, and the time at which they joined, the longer they've been part of that halo, the longer time there has been for those interactions to have occurred. But it's still a little bit individualistic. It's not a predictive process. It doesn't happen to every galaxy. And so there's some really interesting stochastic processes occurring there. Okay, so there's my conclusion slide. I'm excited to be continuing some of this more environmental focused work at Northeastern next year. If you want to see the paper where I've sort of validated this radial distribution of star formation, comparing them to observations, that's there. And then hopefully, maybe by this summer, I'll have published the paper with the other work that I've shown you.
Yes. While people are thinking about questions, I have a question. So for the low mass galaxies, how do you decide when to place the black hole seed and like what's the mass of the black hole that you start?
Yeah, so I just want to be clear, I'm not part of the TNG team, so I don't decide where the black holes are seeded, but I think they're seeded at, I want to say 10 to the 6 solar masses is the black hole mass when they're seeded, and it's when the halo reaches a specific mass. And so if the satellite joins a host halo, before they've achieved that mass on their own, they don't get a black hole seeded in them. And so, yeah, so there's some interesting effects there. But yeah.
So the positive age gradient in the outer skirt looks very interesting, but you only show that up to 1.5 effective radius. So how does it look like if you extend that to an even longer radii? So I think there have been a lot of observations maybe 10 years ago on local galaxies showing that there are a lot of a U-shape, which is a positive age gradient in the outer skirts. And this sometimes correlates with a downbending break in the outer skirts. Do you also see that in your simulations?
Yeah, I haven't extended out the radii much further. Some of these computations are pretty computationally expensive, and so the larger area that I'm looking over, the more time it takes. But that, I think, is definitely something to look into further, is out to larger radii. Yeah.
Okay, and another question is then, what's the time scale to get to this kind of positive gradient?
That's a good question. And it's something that I'd like to look into a little further. This is my work next year that I'm hoping to do, is looking a little bit more at those timescales for when the satellite enters the halo, how long does it take, but it's not very, let me see if I have, sorry, I have like 5,000, okay. So here I'm showing the joining redshift plotted as the color bar here. And so you can see there's quite a bit of scatter in terms of the quenched galaxies, where some of them are getting quenched pretty quickly upon infall, and some of them are taking quite a long time. I mean, you even have some main sequence galaxies that have been part of the halo for a really long time, and just haven't quenched yet. So I think it kind of depends. We had a talk, I think yesterday, we were talking about the angle on which the satellite's orbit is carrying them. And so there's a lot of different factors that can come into actually quenching these galaxies within the halos.
Thank you.
I think in the interest of time, let's thank our speaker again. We have the flash talks.
Go ahead. Do I speak here? Do I speak here?
Yeah.
Oh, okay.
Or you can take the mic here.
Oh, yeah, yeah.
Okay, I'm Osase and I'm a PhD student at the CFA. So this week we've discussed how great it would be to be able to resolve the CGM to better understand the baryon cycle. And I just want to emphasize that a huge wealth of work exists that's already done this for the most massive galaxies in our universe, which are located at the centers of galaxy clusters. Of course, at such high mass scales, the baryon cycle here is mostly the AGN feedback cycle. And from multi-phase observations, we've learned that radio AGN, the red, can not only push gas out of the galaxy and heat the surrounding atmosphere, but they can also entrain gas as they do so, which will eventually rain back down onto the galaxy to power new star formation and black hole accretion. And which is like generally just a completely stunning result. And we've seen this in like several systems, dozens of systems. And so it paints this picture of this really tight and gentle feedback loop that's persistent throughout these clusters. So for my work, we wanted to understand how mergers, which are key for galaxy and cluster growth, may impact this very tight feedback loop. So we chose 1531 as our case study because in addition to this really beautiful blue beads on a string star formation, you also have these two giant galaxies that are crashing together in a very friendly embrace. And so with Chandra, we can see the hot intracluster medium, and the most interesting structure is these two wings right down there that are kind of faint. But when we go to the low frequency radio regime, we see it's actually the opening to an incredibly massive and old radio AGN lobe. And so we think that this lobe is a relic of an AGN outburst that occurred over 150 million years ago and injected a ton of energy into the cluster's atmosphere, so much so that it's actually the third most powerful that we've ever observed. So we also see this dense multi-phase gas draped around the rims of the radio lobe, and it's pretty much sure we're pretty sure it's the fuel for the star formation and the pretty beads. So what's the role of the merger? So we think tidal forces stimulated the star formation and enhanced the ram pressure forces to separate the cold and warm gas phases, and has delayed it from being reaccreted by the supermassive black hole, which explains why it's currently inactive. So if you want to see more pretty pictures, I really encourage you to check out the QR code and check out our paper. And if you have the energy, you can come and find me to learn about the messy details and our several open questions. But yeah, thank you.
Hello everyone, my name is Sachi Veerasurya. I'm a postdoc at Carnegie Observatories, and today I'm going to tease you about the curious case of Centaurus A. Now, why is Centaurus A interesting? It has an AGN, and it went through a major merger about 2 gigayears ago. And interestingly, if you look at the observed luminosity function in Centaurus A, it begins to steepen as you go inwards towards the center. And what's causing this quenching effect is not known. So we want to investigate this case by modeling dwarf galaxies in Centaurus A system using the semi-analytic model Galacticus. And yes, it's named after Marvel villains, so please don't sue us. So we are able to reproduce this luminosity function and the overall satellite population of Centaurus A satellites in this region using the same physics that reproduce the Milky Way satellites in Veerasurya et al. 2023. But we cannot reproduce the steepening effect in the luminosity function within 150 kiloparsec. So what's causing this? We tried quenching star formation at cosmic noon, and this in fact can reproduce the steepening effect. So this leads us to question whether we can link this AGN to this quenching effect. And if you want to find out more, please come talk to me and we can solve this mystery together. Thank you.
Well, the discovery of supermassive black holes and massive galaxies that are quenched at redshifts greater than 4 have challenged our understanding of the rapid growth and quenching in very short time scales. And in the context of the lambda CDM model, this has been surprising discovery. And so AGN positive and negative feedbacks depend on the temperature and mostly on the density of the gas. And since the size, at redshifts greater than 6, the conditions are very different than in the local universe. Namely, for instance, the the volume density of gas can be hundreds or thousands of times that of the local universe. Black hole positive feedback in the local universe is rare, but much more frequent in the early universe. And here I show a microquasar that is a stellar mass black hole in our galaxy at a distance of 6 kiloparsecs, inducing very clearly star formation. And it's a good target for the James Webb, because it's only 6 kiloparsecs, and if one is interested in the physics, the resolution there will be incredible compared with AGNs. And there, this positive feedback is seen in all redshifts, and also negative feedback. Please, the second one. Okay. Also, enhanced star formation is a second physical mechanism than the enhanced star formation and galaxy growth that is observed from the local universe up to very high redshift universe. And the conclusion is that AGN feedback and gas-rich mergers at redshift greater than 5 are a key physical processes that enhance star formation, inducing the observed rapid growth and later quench of massive galaxies. The progenitors of massive galaxies are very likely the extremely compact, dusty red galaxies observed at redshifts greater than 5. And in the first galaxies, supermassive black holes seem to grow more efficiently than the stellar population in those galaxies. And it's intriguing, there is the intriguing possibility that black holes came first and stars later. This is a possibility to explain the relative high mass of black holes relative to the stellar populations in these very high redshift galaxies.
Okay, so I'm first going to give the briefest of overviews for why we even might want to look for intermediate mass black holes. So these are a selection of seeding mechanisms for the growth of supermassive black holes, which predict some different scaling relations, particularly in the intermediate mass regime. So obtaining a better census of these sources is a test for these seeding mechanisms, and that helps us better understand galaxy black hole coevolution across cosmic time. So where can we find intermediate mass black holes? Again, turning to our scaling relations, we expect these might preferentially populate metal-poor dwarf galaxies. This actually, though, presents some problems for cleanly detecting intermediate mass black holes. So in these galaxies, of course, we can have bursty star formations, histories, low metallicity stellar populations, and this means that the intermediate mass black hole itself might provide only a small fractional contribution of the total ionizing photon rate. So if you look at typical emission line diagnostics that we use to select AGN, these might fail to actually detect that there's a presence of an intermediate mass black hole in the context of this star formation at low metallicities. At low metallicities, we also know that luminous X-ray binaries form more efficiently, so these could be also a potential source of contamination in your search for intermediate mass black holes. So to address some of these issues, we have a suite of photoionization simulations where we're coupling simple stellar populations at a range of burst ages and metallicities, self-consistently with ultraluminous X-ray sources, and intermediate mass black holes for a range of black hole masses and AGN fractions. And we're interested in exploring diagnostics that are more sensitive to the presence of an intermediate mass black hole in this regime of low metallicity star-forming dwarfs. So just as you look in these diagrams, some preliminary results on the right here. If it's light blue, it means it's not working at detecting dwarf AGN. Dark blue is better. So some of these are not ideal, still at low metallicities, or they suffer from ULX contamination. They potentially only work for higher AGN fractions, or they work well, but it's a weaker line, like a neon 5, maybe not always detected. We're finding some things that are potentially much better. And just to plug for JWST, we're finding a lot of power in the mid-infrared, potentially for cleanly detecting these sources. So please reach out with any questions. Thanks.
That's it. All right, I think we are done with the session. So do you have any announcements?
Just to remind you to check the posters and to check the e-posters in the cafeteria, and that this afternoon we will have our workshop. So please stay also for that. And now we will have a coffee break till 11, right? And then we will have the last two talks and the discussion and the final remarks. Thank you very much.